Hello, Dr. K here, and we're going to cover homework 3 with this video. So I'm going to open up the share application screen. And we're going to go to study plan. We're going to cover section 6.8 today. Essentially linear inequalities in two variables, and then systems of linear inequalities in two variables. And the systems can be more than two inequalities. You'll see there might be several. And it's leading up to linear programming, which is the end of section 6.8. So let's go ahead and start with the definition, which is a half plane. In one dimension, the solution to an inequality was a half line, because we were greater than a number, or if it was a single inequality like x greater than 2, then it was a half line on the right side of the number 2. And you would put a circle or a dot depending on the sign, the inequality sign. So in 2 dimensions, the solution is a half plane. It's either side of a line. So the set of all points in a plane on one side of a line is called a half plane. And that's going to be the solution to an individual inequality in 2 variables. Because when you have 2 variables, you have essentially you have the possibility, definite possibility of a line being generated to split the plane in 2 parts. When graphing an inequality in 2 variables, if the inequality contains either of the inclusion symbols, then we use a solid line. Just like if it were one variable, we would use a dot, inclusion. It's a solid dot or a solid line, solid circle, whatever they call them. And then number 4, the set of points that satisfy all inequalities in a system of linear inequalities is called, naturally, the solution set. So a half line was the solution to an inequality in one variable, x, for example. Now the solution is going to be a half plane. It's a set of ordered pairs that are on one side of a line or the other, and including the line or not, depending on the sign. So let's go ahead and jump up to number 11. So when we go to test which side of the line or is the half plane that we're interested in as a solution, we usually need a test point. And the easiest test point is the origin, which is the point 0, 0. And we can use that provided that the line doesn't go through the origin, which happens vast majority of the time. So they're going to ask us to plug in 0, 0 to each one of these 4 inequalities. So what happens is in letter A, 3 times 0 is 0 and 5 times 0 is 0. So the whole left side of the inequality is 0. So the question is 0 greater than 11? And the answer is no. So in that case, we would shade the opposite side of the origin, because the origin doesn't work. As a test point, it failed, because we ended up with a false statement that 0 was greater than 11. So we can't use that point. So it tells us you're on the wrong side of the line. So for number B, now I would have, is 0 less than or equal to 6? Because once again, the whole left side of the inequality is 0. So is 0 less than or equal to 6? And the answer is yes. So now my test point was successful, and I would shade that side of the line. In this case, it's a solid line. In part A, it was a dotted or dashed line. Well, we're going to go through this phase where it takes extra long to load the answer. I'm not sure whose server is going bad. I think it's the Pearson company. It's just that we have to be patient. It'll just keep doing this for a few seconds here. Come on. Well, we could start doing part C, because that's going to come up next. In part C, when I plug in 0, the x and y's are on opposite sides, but nonetheless, the question is 0 greater than or equal to -2? And once again, the answer is yes. No. Okay, so finally, and we said yes for letter C, because 0 is greater than or equal to -2, so yes. And then D is 0 less than 3. And once again, it's yes. You see how easy it is? You just plug in 0 for both variables, x and y. No! Excuse my dog. All right, that was number 11. Now we're going to go ahead and actually graph. So I'm going to open this up, make it larger so we can see it. So now what we have is 2 lines associated with, or I'm sorry, there's only one inequality here. My bad. This is 13, yeah. So we want to graph the solution. So we could treat this like a line. It's the line y equals x minus 6, and it's a dotted line because of it's an exclusion. We're not including the line. So when I hit the line tool, you'll notice on the right here, I have a solid and dashed. Now I hit the bottom dashed. So now I'm set up for a dashed line. And what I'm going to do is just use y equals x minus 6. So I'm going to use the intercept of -6. And the slope is +1. So I go 1 up, 1 to the right. And there's my dashed line. Now to finish this, I have to shade in above the line or below the line, or to the left of the line or to the right of the line, however you perceive it. So if you test the origin, which is right there, you could see that I would get the statement 0 is greater than -6. True. So I go down here to the tools and I hit this paint bucket right here. See, it says, what does it say? Shading tool. And I put it above where the origin is. And there's my solution. It's the half plane above the line. And I check my answer, and they say, good job. So there was 2 things to recognize here. One is that it's a dotted line or a dashed line because of the exclusion symbol. The other is that we got a true statement when we use the origin as the test point. You can use any point that's not on a line. It's just the origin is very handy. It's very useful. It's easy because the algebra involved is simple. You're not really multiplying times a coefficient when you plug in a number for the variable. If we have to, if the line goes through the origin, which we'll see in an example later, I think, we have to pick some other line. For instance, I could have picked the point 2, 2, which is not on the line, and I would have got 2 is greater than -4. Still true. So that test point would have worked. Any point in the yellow region would work, but just kind of passing that on. Okay, let's go to 19. Okay, I'll make it bigger. So here we have y is greater than or equal to 2/9 x minus 4. So now you can see why we were drawing lines in the various mechanisms that we used. It's really simple. Once again, just put an equal sign in there. That's the line you want. So, and this is a solid line because of the inclusion. So I hit the line tool and I leave it. It's queued up for a solid line. So I just leave it. And my intercept is -4. And my slope is 2/9. So I go up 2, +2, and I go to the right, +9. So there's my solid line. And then I use the origin because the line doesn't go through it. So now I get 0 is greater than or equal to -4, which is true. So I hit my paint bucket and put it above the line. And that is the solution for this particular inequality. Oh, here we go again with the slow whirling dervish. I think maybe there's just a whole bunch of people wanting to use their software and it just gets hung up at their end. I'm not sure what else it could be. This happens every once in a while. Just have to be patient. So that was 19. So as we're waiting, you can see that solid line, and we're using the intercept and the slope to draw the line, rather than plotting points or intercepts. We use the one intercept because it's obvious. B is -4, which means it's on the y-axis, and then we use the slope 2/9. Okay, so finally told us we were right. Now we're going to go to problem number 21. There it is. Let me make it bigger. Another example of one equation. Now this one, when we plot this one, you can see that it's a dotted line. So let me set that up first. So I hit the line tool, and then I tell it I want the dotted line below. You can see that's highlighted now. Now this one's easy for intercepts, because if 2x plus 5y equals 10 is the line, the dotted line we want, then the two intercepts are 5, 0, and 0, 2. When y is 0, x is 5, and when x is 0, y is 2. So that's easy enough. So 0, 5, and I'm sorry, 5, 0, and 0, 2, dotted line. And now when I plug in 0, 0, it's true. 0 is less than or equal to 10. So I take the paint bucket below the line. See, this one was set up in general form. So rather than try to use the intercept and the slope, I just used the intercepts on this one. That's why we studied all those different mechanisms to draw lines, just to make it easy on ourselves. Okay, next one up is 27. Okay, this one goes through the origin. How do I know that? Because B is 0 here, essentially. If you were to solve that for y equals mx plus b, it's y equals -3x plus 0. So it goes through the origin, but that's okay. We don't mind that. But first of all, it's a dotted line, so I hit the line tool and I do dotted line. So I know one point is the origin, because if I plug in, if I say 6x plus y equals 0 as the line, then if both x and y are 0, I get a true statement. So the origin's on there. Now I need another point. So why don't I use 1 for x and -3 for y? That'll give me 6 minus 6 equals 0. So 1, -3. So 1, -3. So here I plotted points, essentially. I know that the origin's one of the solutions. And you can see that if I plug in x equals 1 and y equals -3, I get 6 minus 6. Okay, and now I can't use the origin. So let's use the point 2, 2. So if I plug in 2, 2, I get 12 plus 14, or 4 is 16. 16 is greater than 0. So 2, 2 gives me a true test point. So I hit the paint bucket and I go to on that side where 2, 2 is. Okay. Any test point would have worked, just so you know. If I would have gone on this side, let's say -2, -2, then I would have had -12 minus 4 is -16 is greater than 0. That would have been false. So I would have highlighted the opposite side like we did. So it doesn't matter which one you pick, you'll get the true answer if you make your substitution correctly. Okay, we've done just one inequality. Now we're going to do a system. Now we have two inequalities. And the only difference here is that we don't want to really paint in our solution region. And I'll show you why. Let's just draw the two lines. They're both dotted lines. Okay. Now the first line is set up for y equals mx plus b. You got m is 1, b is -2 for the first line. So they're both dotted. So I queue up a dotted line, and I go to -2, and then the slope's +1. So 1, 1. So there's the first top line. Now, I'm going to mentally make a selection here for 0, 0. If I plug in 0, 0, I get 0 is greater than -2. So the origin works for the yellow line, which is now going to be a blue line as soon as I do that. So we're above the blue line. Now I'm going to draw the other line, which once again is a dotted line. So I hit the line tool. It's already queued up for dotted or dash, so I leave it. Now I can use the intercepts for this one. When x is 4, y is 0, and when y is 4, x is 0. You see that? It's pretty simple. So 4, 0, and 0, 4 are the intercepts for this one. So 4, 0, and 0, 4. And now it's a yellow line. So I'm going to leave it yellow for this discussion, because now when I plug in 0, 0, I get zeros less than 4. The origin works again for the yellow line, and it worked for the blue line. So see, the thing is, there's 4 regions here. The yellow and blue line create 4 regions, 4 possible regions of solution. So the solution now is no longer a half plane. It's the intersection. Well, it's a region. It's one of 4 possible regions. And since we already tested and said that origin works for both lines, so that this is the only possibility. So that is the solution, that region. Okay, that was 29. Let's do 33. Sorry about the delay. Okay, so we're going to do 33. So these are both solid lines. Notice how I check out whether they're solid or dotted right off the bat, so I know. Sometimes they're one solid, one's dotted, but typically they're both the same. Just have to check. All right, so I hit the line tool, and it's queued up for solid. If you look at the first equation, I can do intercepts. I have to if you have to, right on the side, x minus 4y equals 4. So the one intercept is easy. When y is 0, x is 4. Oop. Line tool. Okay. Now, when x is 0, you have minus 4 equals 4, so y equals negative 1. So negative 1 is the intercept for y. So I plotted points, actually intercepts. So once again, when y is 0, x is 4. However, when x is 0, I have minus 4y equals 4, so y has to be negative 1. Okay, for the yellow line then, let's plug in 0, 0, and we get a true statement. 0 is less than or equal to 4. So we're above the yellow line. Now I need a line tool. I'm going to draw a solid line for the second one. It's very similar to the first one. When x is 0, I'm sorry, yeah, when x is 0, you have 5y equals 5, so y equals negative 1 again. And then when when y is 0, x is 5. So look at that. They're pretty close to each other. Oop, I made a mistake there. I'm going to start over. Okay, there's the first one. The first one's correct. Let me redo the second one. So I need a line tool, solid. Okay, when x is 0, y is 1. My bad. See, I said minus 1. If you just eliminate in the second inequality, which is you're writing it as an equation, you have x plus 5y equals 5. If x is 0, you have 5y equals 5, so y equals 1. Now, when y equals 0, x equals 5. So I was on the wrong side there. They're still pretty close, but you can still see the 4 regions. Now, for the yellow line, I can use the origin, and when I plug it in, I get 0 is greater than or equal to 5, which is not true. So we're above the yellow line also. We're above both the blue and the yellow, which means There's only one region that does that, and that's up here. Okay? So that was 33. Let's try 39. See what's going on there. Oh, okay, this is a feasible region. We're going to go ahead and get into linear programming. So I'll tell you what, let me do this. Let's go back to pick up some terminology that we need. So first off, 687. In linear programming, the shaded region formed by graphing the system of inequalities is called, we call it the feasible region. It's where the solutions to our objective function lie. It's called the feasible region. I'll go through these definitions and then we'll open up the book for a second and see if we can find some of these examples. The points of intersection of the boundaries of the feasible region are called the vertices. Another name's corner points. So if I say corner points, I mean vertices. It's the points of intersection for the regions. So far, we've only had one intersection point because we only had two inequalities, but that's going to change. And then number 9, in a linear programming problem, the function used for the quantity that is to be maximized or minimized is called the objective function. There's some objective that's usually cost or profit or something, usually with money involved, not always, but typically you're objectifying something and you want to maximize it or minimize it so that you can know how to proceed with your planning. Okay, so we've been here before. Let's go ahead back to that one that I stopped, 639. Okay, 839. Where'd it go? Okay, there it is. So this is a feasible region. Now we can't see this, but there's 4 inequalities that were used to make this region, and you see there's 4 corner points or 4 vertices. Now all we see is the lines from vertices that join the vertices, but those lines are inequalities, the lines associated with inequalities that extend both directions. This one here is y greater than or equal to 0, and this one here is x greater than or equal to 0, because those are horizontal and vertical lines. So the vertical line is x equals 0, but it's to the right, so it's greater than or equal to 0 as an inequality. And this is above the x-axis, so it's y greater than or equal to 0. And here's our objective function. We want to get a maximum and then a minimum for this objective function, whatever k is. So an easy way to do this is to have the calculator. And just use the calculator. And so I would just go starting at the origin, which is pretty simple. I mean, I'll include it just for the sake of including it. So it's 6 times 0 plus 2 times 0, because both x and y are 0. So obviously k is 0 at the origin. And then I go counterclockwise. So if I just hit second enter, then I just have to change this x equals 0 to x equals 4. And so there k is 24. And then if I do second enter, I can change the x to a 2 and the y to a 4. And at the third point, the point 2, 4, k is 20. And then lastly, second enter, if I change x to 0 and y to 6, I get k equals 12. So the maximum value there of those 4 numbers is 24. So the maximum is 24. Because you can only have a maximum or minimum for the objective function at a corner point, at a vertex. And the maximum occurs at 2, 4. Oh, no, I'm sorry. I picked the wrong one. Luckily, we have a second chance. It was the second point, which means it was 4, 0. I don't think I was paying attention very well there. 4, 0. Okay, and the minimum is 0. The origin won't always be included in your feasible region, but for this one it is. So the origin is where the minimum occurs, for whatever it's worth. All right, so that was number 39. We're going to do the same thing now with 41. Let me see if I can make it a little bigger here. So this one contains 5 inequalities that form a pentagon. Well, yeah, it's a pentagon, 5 sides. So let me clear this. It's 6x plus 4y this time. So I'm going to start here at 30, 10 and work around counterclockwise. So the first value is 6 times 30 plus 4 times 10. 220. Hit second, enter, change the 30 to a 60, and the 10's okay because it's on a horizontal line, so y stays the same. Then I go up to 60, 30. Now I'm on a vertical line, so x stays the same, but the y changes to 30. And for the third point, it's 480, and then I do second enter. Now they both change. X is 20, and y is 50. And so I better write down 220 for the first one. So I don't, because I'm going to lose it here when I go to the fifth. So the fifth one is 2030. So when I hit second enter, I just change the y to a 30 because x is, so the last one's 240. So one that's missing is 220. That's going to be the minimum. So the maximum's 480 at the third point, right? The third point was 60, 30. 60, 30. The minimum was the first one, which I wrote on the side, 220, which occurred at the first point, which was 30, 10. All right. I didn't mean to hit next question so fast, but that is essentially how we, the last two problems give us as example of how we tabulate the values for the objective function. So now I'm going to go ahead and make this large, so I can just make this as large as I can here, this graph or this plane. Now you see we have 4 constraints, and the p is obviously an equals. That's your objective function. So the first 2 constraints that I draw are the x greater than or equal to 0 and the y greater than or equal to 0, which means we're in the first quadrant. See, if y equals 0, they're all solid lines too. You see, they're all inclusions. So I leave it solid. So I have the y-axis, and I'm to the right of the y-axis. Then I draw the line tool again, and then I do the x-axis. And we're in the first quadrant because if x is greater than or equal to 0, that's to the right of the y-axis. And if Y is greater than or equal to 0. That's above the x-axis. So we're in here. We're in the first quadrant. And now I'm going to draw my other two constraints. We'll start with the top. X plus y is less than or equal to 8. So I need a solid line. Now this is easy. They're both intercepts are 0, 8, and 8, 0. If I look at the line x plus y equals 8, the two intercepts are straight up. So x equals 8, y equals 8. So it's this line. And if I test the origin, I get zeros less than or 8. Zeros less than or equal to 8. So we're in the triangle because we're in the first quadrant, but we're below the triangle because the origin, I can use the origin for this diagonal line because the origin's not on that line. So now you see I have a triangle, but everything's extended. We don't get a nice pretty triangle without all the other extensions because that's just the nature of how these work. The other two problems we did were nice and clean because they had gotten rid of all the excess. Now for my second line, or my second inequality, it's also solid. 2x plus y equals 12. Well, I can use the intercepts. When x is 0, y is 12. And when y is 0, x is 6. And once again, for the yellow line, if I just put in 0, 0, I get a true statement. So we're to the left of the yellow line, which means now we're in this region right here. So I'm going to go ahead and that's our feasible region where the yellow is. And you see we have 1, 2, 3, 4 vertices, 4 corner points. And where those two diagonal lines cross, it's a lattice point. It's 4, 4. I don't have to solve for it. You can look at them and you can see that if I plug in the first equation, the first equation 4 plus 4 equals 8. The second one I get 8 plus 4 equals 12. So 4, 4 satisfies both of the lines that we drew. So I'll check the answer. And yes, that's our feasible region. Now we have to maximize and minimize our objective function. So now I need the calculator. And we'll start at the origin. Actually, we don't need to. We know that there's no constant in there. So 4 times 0 plus 5 times 0, p is 0 at the origin. So we'll go here to this intercept 6, 0. So when x is 6, you get 4 times 6 plus 5 times 0 for completeness. P is 24 at the x-intercept down here. And where they cross at the 4, 4, I do second entry, and I can leave the x equals 4 because it's still 4. Oh, I'm sorry. No, my bad. What am I thinking? X is 6, so I got to change the 6 to a 4. So now they're both x and y are both 4. And so p is 36 at this point of intersection. And then the last one, x is 0, y is 8. So when I hit second, oh gosh, when I hit second enter, we said x was 0 and y was 8. And it turns out that the third point is the maximum. Oh, I was way ahead of what they wanted. They wanted the corner points. Okay, so type an ordered pair, the vertices for the feasible region. Okay, so we'll start at the origin, 0, 0. Now, it says use a comma to separate the answer. So I need a comma between the parentheses. And so the second point was 6, 0, comma. And the third point was 4, 4, comma. And then the last point was 0, 8. You notice there's 4 ordered pairs there for the vertices, but there's commas between them. Oh, patience. There it is. Okay. So we have the right vertices. Now the maximum, which we already did, is 40. I was a little bit ahead of the game there, but that's okay. And that occurs at 0, 8. the minimum, which they'll ask us for, is 0, which occurs at the origin. It's kind of a giveaway. You don't want to miss these. Pretty simple when the origin's involved. It's not always the case, but for some of these, they include the origin. Pro forma, I'm not sure why. And that minimum occurs at the origin once again. All right, so 0, 0. Don't forget the parentheses, ordered pair. And spinning is getting a little, okay, so we were done with that one. Okay, that's good. Okay, so that was 43. Let's do 47. A little more complicated, just a tad. Notice that they give us more room for the first quadrant. We really didn't use anything except the first quadrant on the last one. But okay, so now look, I don't have x greater than or equal to 0 and y greater than or equal to 0, but I still have vertical and horizontal lines, and I like to get those out of the way first. So x greater than or equal to 2, and they're all solid lines. You notice the first, fourth, the constraints, the inequalities are all inclusions. So the first one is x greater than or equal to 2. So here's x equals 2. So we're to the right of that yellow line. And then the next one is y greater than or equal to 3. So here's y equals 3, the yellow line. We're above it. So we're in this rectangle or square, this rectangle on the upper right where I'm circling. Now I'm going to draw my inequalities. So the first one, we'll plot points. It's going to be a little hairy here, but we can do this. It just takes a little bit of finagling. So once again, it's a solid line. So the first one is 2x plus 5y equals 33, and the second one is 6x plus 3y equals 33. Let's do the first one. 2x plus 5y equals 33. So I have to plot points because I can't use intercepts. It's obvious to me I can't use intercepts. But look, if I let y be 3, that's 15. And 15 from 23 is 8, so x equals 4. Because 4 times 2 is 8, 5 times 3 is 15. You add them together, you get 23. So that one was pretty easy. And the second one, if I just let y be 1, then that leaves 18. So now x equals 9. So when x equals 9, you get 18. Y equals 1, you get 5. You add them together, you get 23. So I'll tell you what. Let me do this. It's probably easier if I go ahead and, let's see. Yeah. Just temporarily show you what I did there. So what I'm going to do is on the whiteboard, boy, it's really slow. Okay, on the whiteboard, we got 2x plus 5y equals 23. Now, since 23 is odd, no matter what I put in for x, I get an even number. So I got to make sure that for y, I put in an odd number. So you can see that. That's why I chose 1 and 3 to keep 5y as odd. So that when I subtract it from 23, I get an even. So when y equals 3, then 5y is 15, which leaves 8. So x has to be 4, because 8 plus 15 is 23. Oh boy, what happened? Okay, now when y equals 1, I get 5, and that'll leaves 18. So that's x equals 9. Now, those are the 2 points. Let's do the other one here while we have the whiteboard so we can get those, see how difficult it is or how straightforward it is. So for this one, it's the same idea. since 33 is odd, I want to keep y as an odd number. And so the easy one I can see right off the bat is if y is 1, then that leaves 30. So x has to be 5. Because that, y 3 times 1 is 3, that leaves 30. So that leaves 5 times 6 is 30. Oop, that's a nice 5. There we go. So 5, 1. Another one would be, let's see. Yeah, if I let y be 5, that's 15. And that leaves 18. So x equals 3. So there's my ordered pairs for both lines. Notice they're not intercepts. I'm plotting points here because that's the easiest thing to do. All right, so I have my points. I've got them written down. So I'm not going to come back to this screen. So just so you know, I'm going to go back. I'm going to go back to sharing the application screen and go back to the problem. Pain, huh? It's a pain. Open it up. There we go. Okay, so we have our horizontal and vertical lines, and now we want to draw the top line. 2x plus 5y equals 23. We said 4, 3, and 9, 1. So 4, 3, and 9, 1. Now, we are in this rectangle. Now look, it says 2x plus 5y is greater than or equal to 23. If I use the origin for this line, I get 0 is greater than 23. So that's false. So we're above the yellow line. So we're up here. We're in this, still in this rectangle, but we've lost this little triangle. So we're up here in this uppermost region. And now we're going to draw our second constraint, which is 6x plus 3y, and it's going to be 5, 1, and 3, 5. So 5, 1, and 3, 5. Okay, so for this yellow line, if I use 0, 0, I get a true statement. So we're to the left of the yellow line, which means we're in this little triangle right here, because we were up here to begin with. We lost this little triangle, and now we lost everything up here because that's just the way the arrows were facing. So this is our feasible region, and there's 3 corner points, three vertex. Okay, so they're going to ask us what those are. So determine the vertices. So if I start here, that's the point 4, 4. I'm sorry, 4, 3. X is 4, Y is 3. Is that obvious? X is 4, Y is 3. Okay, so 4, 3. Comma. The next point, if I go up here, it's a lattice point. It's X equals 2, Y equals 7. So it's 2, 7. Oops. 2, 7. And a comma. Now the last point is not a lattice point. See this one right here? It intersects between, but I know x equals 2, and I'm on the first constraint. I'm on the top line. So if I plug in x equals 2, I get 4 plus 5y equals 23. So 5y equals 19. So y equals 19 over 5. You see, I'm just a little bit less than 4. So 19 over 5. Okay, so x equals 2, comma, and then I can put in a fraction. 19, tab 5, tab, parentheses. Oop, parentheses. There's my 3 vertices, my 3 corner points. You see why I knew that that's not a lattice point right here. Because I'm between 3.5 and 4 on the y. I'm on x equals 2 on the x because I'm right on this vertical line. That's why I know x equals 2. And when I plug in x equals 2 into the first constraint, I get 5y equals 19. So that's how we got 19 over 5. So now I have to go ahead and use the calculator to find the maximums and minimums. Oops, wrong button there. My bad. Where's the calc? There it is. Okay. So we have the corner points written down. So let's just go ahead and we'll start with the first one. 4.74. I'm using the objective functions times x, which is 4, plus 3.59. 59 times y, which is 3. So 2973 is the profit for the first point. Now the second point, if I just hit second enter, I change the x equals 4 to x equals 2 and the y equals 3 to y equals 7. So 3461, and I do second enter. And I can leave the x equals 2. I just have to change the y to 19 over 5. In order of operations, all I got to do is just put it in there. It'll work. I don't need parentheses. So the maximum is 3461. And we're going to spin a while. And that occurred at the first point, didn't it? As I recall. No, second point. 2.7. So 2.7. All right, and then the minimum was at the third point, 2312. If you round out to 2 decimal places, 2312. See, they say round it to 2 decimal places. And that was at the last point, which was 2.19. So 2, 19 tab 5 tab parentheses. All right, so a lot going on there. We really had to plot points. This one, you can see why these will be worth 10 points on the test or on the homework, because there's a lot going on. You have, look, we had 1, 2, 3, 4, 5, 6, 7 answers. And we had a lot of calculations to figure out. We had a lot of work to do getting those lines correct. So this is linear programming. This is what the U.S. Army developed in World War II. And this is how they would know if we were talking here about, say, something to deal with a quantity like how much gasoline we needed. We needed a minimum of 23.12 gallons and a maximum of 34.61 gallons. That would, I'm being hypothetical here. I know it doesn't, it says profit and all that, but this is the idea. Then you would know you don't need 100 gallons and you need more than 23. So you have some range of numbers, so you can, because you have other situations going on where you need to send similar type equipment. So you want to make sure you don't run out or overload. All right, 49. All right, so this one's kind of strange, I got to admit, but we got to go through it. So this one you want to take notes on the side. Ruben's on a special diet. He must consume fewer than 750 calories at a meal that consists of 1 serving of chicken and 1 serving of rice. And the meal must contain at least 250 calories from each source, 250 calories from chicken, 250 calories from rice. So it says in part A, use X to represent the calories from chicken and Y to represent the calories from rice. So I can answer the second two pretty easy. Both of those, it says they have to have at least, so that's greater than or equal to 250, at least. Right? That's how we read that. Now, the first part's obvious now because it has to be, he must consume fewer than 750 calories. So X plus Y, and I'm not sure why they do a dotted line here, but they do less than. So there's my constraints, right? The total has to be less than 750 of X and Y, calories from chicken plus calories from rice. So X plus Y is less than 750, but they're both at least 250. So that's where we get our inequalities. And now they're going to ask us to draw these. Once again, the bottom two are easier to get because they're just horizontal and vertical lines. X greater than or equal to 250. So the first two constraints I'm going to draw are solid lines. So it's 200, 250, 300, 350, 400. So each tick is 50. So X greater than 250 is to the right of the yellow line. And then I do the next solid line, and 250 for Y is right here. And so now I'm above the yellow line, so I'm in this upper rectangle. And lastly, the sum is less than 750. So if you were to draw it's a dotted line this time. I don't know why, but it's a dotted line. So I have to do line tool, dotted line. And the intercepts are both 750. If you just drew the line X plus Y equals 750, so it's 750. So it's 650, 700, 750 for the Y, and 750 for the X. Now, we know we're in that upper rectangle, but now with respect to the yellow dotted line, if I plug in 0, 0, I get true. So we're in this small rectangle right here because we're below the dotted line. So I take my paint bucket and say that's our feasible region. And now they kind of change course on us, and I'm going to have to show you how to do this. It's what it is. It's proportions. It says there's about 180 calories in 3 ounces of chicken. So 3-ounce chicken equal 180 calories. And then there's 200, so 8 ounces rice equals 200 calories. It says for the 0.275275, which is in their feasible region, but it's not a corner point. So they're changing up here slightly, but we can still do this. It says for the 0.275275, determine the number in ounces of chicken. So we set this up as a proportion, 2 proportions. So the first proportion, I'm going to go ahead to the whiteboard again because it's easier for me to show you. So hold on. Let's see if I can get this. All right, so I'm going to erase what we got. And I'm going to show you, it says that there was, with respect to the chicken, 3 ounces was 180 calories. I'm just going to use the numbers. And that equals X ounces of chicken for 275 calories. So you just make 275. You just make a proportion. Gosh darn it. Why did it do that? My computer is being recalcitrant. I'll tell you what, since that's happening, let's go back to the share application screen. We'll just use the calculator. We can do it that way. That's probably easier. So let me get the problem up, and then I'll get the calculator up. Okay, so we have 3 over 180 equals X divided by 275. So we multiply both sides by 275, and we get 275 times 3 over 180. And that'll be x. So let's do the other one. That one, it'll be 275 times 8 over 200, because that's the proportion. But this is for y. In other words, 8 over, that's the wrong number there. 8 over 200 equals y over 275. So now we multiply both sides of there by 275. And so for the chicken, we get, or for the rice, we get 11 ounces. So it represents 4.58. I better look at the calculator again. Yeah, 4.58 ounces of chicken and 11 ounces of rice. Let me see that I put a wrong number in there. Oh, 1 decimal place. That's what it was. So it's 4.6. Number's not wrong. This is where, if you did this on a test, I'd give you credit if you wrote 4.58 instead of 4.6. Happens to the best of us. Okay. So strange problem. It just deals with proportions. It doesn't really deal with corner points, but it's a algebra review. Just do your best on it. There's only one of these. And then we'll do one more here for linear programming, 53. Now, it's set up a little different. We have to find the constraints based on what they wrote, which is not really difficult. Just got to take notes here. So a paint supplier has 2 machines. So X is going to be the number of hours for machine 1. And Y is going to be the number of hours for machine number 2. I got that from below in part A. All right, to meet its contractual obligations, the company must produce at least 60 gallons of indoor paint. So we got 2 different kinds of paint, indoor and outdoor. So indoor must produce at least 60 gallons. So indoor has to be greater than or equal to 60. And outdoor has to be greater than or equal to 175. Now, machine 1 makes 2 gallons of indoor and 14 gallons of outdoor per hour. Right? So machine number 1, 2 gallons indoor and 14 gallons outdoor. Whereas machine number 2 makes 6 gallons of indoor and 7 gallons of outdoor per hour. So I can tell you that, first off, they're both greater than or equal to 0, X and Y. Both machines can't have negative hours. So that's pretty straight up. You could not run one of them, right? You can if you run one machine, that's where the other one could be 0. All right. So for the 60 gallons of indoor, to get 60 gallons of indoor, I would have to run I would get 2 gallons from machine 1, so that's 2x, and I would get 6 gallons from the machine 2, so that's 6y for every hour. So 2x plus 6y is greater than or equal to 60. That's for the indoor. So they told me that there's at least 60 gallons of indoor, and I get 2 gallons from machine 1 and 6 gallons from machine 2 for every hour. So that's 2x plus 6y. Now for the outdoor, it's 175. I would get 14x plus 7y for the outdoor. So the 2x plus 6y is A. That's a constraint. And the 6 14x plus 7y greater than 175 is for the outdoor. So there's my constraints. The other two are just distractors. See, because the 2 plus 14 is part of machine 1, so it can't be a y. And then 6 is part of machine 2, it can't be an x. So that's how you know those two are false. So there's my constraints. All right? Now I just have to determine the objective function. In the last sentence, it says it costs $35 per hour to run machine 1 and $36 to run machine 2. So we want, this is a cost function, and it's 35x, right? $35 per hour for x, that's machine 1, plus $36 for machine y per hour. So there's my cost function to run the machines. And we probably want to minimize this. That's what we're going to try to do. All right, so that's correct. And now graph the constraints. So once again, the first two are easy, are the x and the y. And so they're all solid lines. The constraints are all solid lines. So we have y greater than 0 and it keeps doing that. X greater than 0. Line tool. So we're in the first quadrant because both machines have to be non-negative. Now constraints. So let's do the A first. 2x plus 6y less than or equal to 60. I can do intercepts on that. It's a solid line, so I hit the line tool. When x is 0, y is 10, because 6 times 10 is 60. And when y is 0, x is 30. Look at that, they gave me a 30 here. I can do it. So there's the constraint for the part A. And then I plug in 0, 0, and I get false. So we are above the yellow line. We are up here in this region. Now I do the second one, 14x plus 7y. This one's a little more difficult. I can get the y-intercept. There's 7 quarters and $1.75. So the intercept for the y is 25. When x is 0, y is 25. And the other one's going to be a little more difficult. Let's see what I can do with that. If I let y be 5, that's 35, and that leaves 140, so x is 10. So 10, 5 would be the other point. So 10, 5. Right, the second point for f. If x is 10, that's 140, and y is 5, that's 35. You add them together, you get 175. Okay, so for the yellow line, once again, I use the origin. I am to the right of the yellow line. So we're up here. This is what we call an unbounded region. And guess what? We still have corner points or vertices. We have this one, 0, 25. We have 30, 0, and we have the point of intersection, which is a lattice point. And we know that that's, we can just read it off, 9, 7. X equals 9, y equals 7. And if you plug them in, you see they both work. Let's see, is that right? Yeah. 18 plus 42 is 60. And 126 plus 49 is 175. Yep, they both work. So the point of intersection right there is 9, 7. I could work it out algebraically, but if it's a lattice point, you can see where they both intersect right there, 9, 7. So we graph the constraints, and this is unusual because usually we've been having what we call a bounded feasible region, like this little area down here. It's bounded because you can draw a circle around it. This one goes on to infinity, but all we're interested in is the corner points, and there's 3 of them. 1, 2, 3. So they want us to determine the vertices. So we'll start at the upper one. So that's 0, 25. Then put a comma. We said the second one was 9, 7. Comma. And the last one is 30, 0. So here's the thing that's going on here. You either run the first machine for 25 hours alone, You run the second machine for 30 hours alone, or you run both of them, machine 1 for 9 hours and machine 2 for 7 hours. Now, that's probably, you're better off because you're running them like a fraction of what you would normally run each one alone. So you want to run both machines. Let's see if that gives you the lowest cost. I'm pretty sure it does. Let's see if that's true. First of all, we got to check the feasible region. It's going to spin. Okay, so we got the right answers. And it says, how many hours should each machine be operated to fulfill the contract at minimum cost? So it is a minimum. So I open up the calculator and I got to calculate these values. So it's 35x. Let me clear that. So 35x, and we're going to start at the first one, which is 35 times 0 plus 36 times 25 for the y. So that's $900 just to run machine 2 by itself. And then I do second entry. The second one says run machine 1 9 hours and machine 2 7 hours. And for that, the cost is $567. And the last one is to run machine 1 by itself for 30 hours. So that'll be 30. And just for completeness, I'll put the 36 times 0. Even though we know that doesn't. Wow. Yeah, so it's a whole lot cheaper to run the two machines in conjunction, unless one of them's broken. So we would operate machine 1 for 9 hours and machine 2 for 7 hours. And they're probably going to ask us what the minimum, the minimum cost, $567, wasn't it? Yep, $567. Oh, I got too many fives in there. See, my fat fingers. I put 5,500. It's 567. I was wondering why I marked it wrong. All right. So that's it from linear programming. So you can see how it works. I trust that you'll be able to get a lot out of this video. There are some other video. Some of these problems have their own videos also listed in your what am I trying to say? Blackboard. Yeah, your Blackboard course. So there's a couple ways to watch these. And then next Tuesday, I can answer questions. But if you need questions answered before then, by all means, text me or email me, and I will try to answer your questions. Okay, so I hope this was useful, and I look forward to seeing you all Tuesday, and I'll hear from you sooner if otherwise. Okay, this is Dr. K, and I am going to sign out.